You know that glowing appliance sitting on your kitchen counter right now? Most of us just fill it up, hit a button, and kind of assume it's doing some basic filtration, right? Well, I want to challenge that assumption right out of the gate. Is your water pitcher really just a simple filter? Or is it actually a miniaturized, highly sophisticated electrochemical reactor? Welcome back, everyone. I am so glad you're joining me for this explainer today. We are taking a really fascinating journey from everyday hydration straight into the absolute cutting edge of molecular engineering. We're getting under the hood of the modern hydrogen water pitcher. Honestly, it's a brilliant piece of technology, and I am literally thrilled to break down exactly how it ticks. All right, let's dive right in. Okay, so here's our roadmap for today. First, we'll go beyond the alkaline era. Then we'll step inside the electrochemical reactor. After that, we'll look at the race for supersaturation, figure out how we're overcoming physical bottlenecks, and finally, we'll gaze into the smart hydration horizon. Let's get to it. Section 1. Beyond the alkaline era, from scale to science. What's super interesting about this whole transition is just how stark the contrast really is. I mean, historically, electrically modified water meant those mid-century alkaline ionizers. You know the ones. They required the natural minerals in standard tap water just to conduct electricity. And the result, well, they totally altered the pH to be highly alkaline, and man, they were notorious for building up this heavy, crusty calcium scale right on the electrodes. Not great. But look at the modern PEM and SP pitchers. This is a massive paradigm shift. They don't mess with the pH at all. It stays perfectly neutral. And because they use advanced membranes, they can run on purified, reverse osmosis, or distilled water. That means absolutely zero scaling. The whole focus has completely shifted away from altering pH and purely toward generating dissolved molecular hydrogen. Moving right along to Section 2, inside the electrochemical reactor, or as I like to think of it, fuel cell tech running in reverse. To really get this tech, we have to talk about the molecular gatekeeper sitting at the absolute center of the whole operation. That's the SPE and PEM, the Solid Polymer Electrolyte and Proton Exchange Membrane. It's often made from a highly specialized material called Nafion, and it's honestly ingenious. Think of it as a super strict physical bouncer. It completely blocks electrons and gas from crossing over, but it selectively lets positively charged protons just slip right on through. That separation right there, that's the heart of the entire system. Now, flanking that membrane are the electrodes, and trust me, engineers are not cutting corners here. They're using pure titanium substrates, heavily coated in premium platinum or sometimes even iridium. Now, you might be wondering why use such crazy expensive platinum group metals? Well, it's definitely not just for show. They act as absolutely indispensable electrocatalysts. Basically, they dramatically lower the activation energy needed to literally rip water molecules apart. Without that premium coating, the whole device would just be incredibly inefficient. Okay, so here's the actual molecular magic trick happening inside the chamber. Step 1, over at the anode, water gets oxidized and broken down. The electrons travel around the circuit, while, step 2, those protons slip directly through that PEM membrane we just talked about. And here is what's absolutely critical for your health. Step 3. The byproduct oxygen and any trace amounts of ozone are completely isolated and expelled right out through a waste vent at the bottom of the pitcher. Finally, step 4, over at the cathode, the protons and electrons recombine to form pure molecular hydrogen, which then dissolves straight into the drinking chamber above. That strict mechanical separation means there is absolutely no way ozone is getting into your drink. All right, Section 3, the race for supersaturation. Let's dig into the actual metrics of success here. 1.6. Keep this number locked in your head, because under standard atmospheric pressure and standard room temperature, physics sets a very hard, totally unforgiving limit on exactly how much hydrogen you can dissolve in water. And that hard limit is 1.6 parts per million. So the reason for that strict 1.6 boundary is Henry's law. You can kind of think of Henry's law as the ultimate bouncer of chemistry. It dictates that the amount of dissolved gas in a liquid is directly proportional to its partial pressure right above that liquid. So in just a normal, unpressurized cup of water sitting there on your counter, 1.6 parts per million is literally all the hydrogen it can physically hold before the gas just goes right ahead and bubbles out into the air. But hey, engineers love to cheat the rules, right? And the way they do it here is just brilliant. High-end modern reactors actually break right past Henry's law. They do this by sealing and pressurizing the electrolytic chamber, which generates what are called nanobubbles. And because these nanobubbles have incredibly low buoyancy and a much higher internal pressure, they just stay suspended in the liquid for a lot longer.
That little trick allows these devices to achieve a supersaturation of 3.0 parts per million, or sometimes even beyond that.
Now, the other really major metric of success we need to look at is ORP, or oxidation reduction potential. Just consider the comparison for a second. Standard tap water usually has a positive ORP, usually sitting somewhere between plus 200 and plus 400 millivolts. That tells us it's a highly oxidizing environment. But hydrogen water? It features this dramatic, highly negative ORP, often landing between negative 400 and negative 600 millivolts. That massive shift happens entirely because the dissolved diatomic hydrogen acts as a super powerful electron donor in the water. It's a total game changer.
Which brings us to Section 4, overcoming physical bottlenecks. Because despite all this brilliant engineering, we are still battling the unforgiving laws of physics. There are basically three main villains in the world of hydrogen generation that are constantly threatening both the efficiency and the lifespan of your hardware. We've got gas volatility, membrane fouling, and electrocatalyst lamination. Let's break these down real quick.
First up is what I like to call the Great Escape. Molecular hydrogen is literally the smallest molecule in the known universe. So naturally, it is the ultimate escape artist. It rapidly diffuses through almost anything, plastics included, and escapes right back out into the atmosphere. Honestly, even if you have that super-saturated 3.0 ppm water, it's going to drop right back to baseline in just an hour or two if you leave it exposed. So it's a total race against time. You basically have to consume it immediately or store it in a vacuum-insulated stainless steel container with absolutely zero headspace. Now, the next two villains actually attack the hardware itself. Fouling happens when people mistakenly use hard tap water, which permanently destroys the membrane's conductivity. The calcium ions literally bond to the membrane and ruin it. Done. Then you have delamination. That's caused by the violent, continuous generation of gas bubbles combined with thermal expansion. Over thousands of cycles, that process literally rips microscopic layers of that ridiculously expensive platinum coating right off the titanium base. So yeah, routine maintenance and really advanced manufacturing are totally essential if you want to fight these off. Finally, let's look at Section 5, the Smart Hydration Horizon. We're zooming out a bit here to ecosystems and AI. Look, these devices are no longer just isolated, dumb kitchen gadgets. They are fully interconnected nodes in the modern smart home. The old utilitarian plastics? Gone, replaced by food-grade, high-borosilicate glass and premium tretan to completely prevent any chemical leaching under electrolytic stress. But more importantly, check out the full IoT integration. These things sync seamlessly with Google Home for voice-activated morning routines. They connect to Tapo smart plugs to kill phantom power and save your electrodes. They even use Wiz API hooks to change your ambient kitchen lighting to a cool blue the exact second your water hits optimal hydrogen saturation. How crazy is that? And let's zoom out even further to see how this builds out in the commercial space. Multi-branch food and beverage operations are now deploying literal fleets of these smart pitchers. They're using centralized databases and custom apps to track daily telemetry. We're talking cycle counts, voltage variance, total volume processed, the whole shebang. Facility managers get automated alerts for preventative maintenance and membrane replacements. That ensures that every single customer is getting the exact same standardized, high-quality hydration output no matter which branch they happen to walk into. Which brings us right to the absolute state-of-the-art horizon. Engineers are already looking at the next major leap, literally embedding edge AI processors directly into the pitcher chassis itself. These processors are being designed to analyze real-time water impedance and atmospheric pressure so they can dynamically adjust the voltage on the fly, perfectly optimizing the Nernst equation for maximum hydrogen yield. They're even developing these wild piezoelectric transducers to create ultra-fine nanobubbles that could potentially stay suspended in the water for days rather than just a couple of hours. Which leaves us with this final, kind of provocative thought. As these devices integrate deeper and deeper into our digital health APIs, we really have to ask, will your kitchen soon predict your physiological recovery? Just imagine waking up and your smart pitcher has already pulled the biometric data from your sleep tracker, automatically tailoring the exact ORP and hydrogen concentration of your morning water to your specific real-time recovery needs. It sounds like science fiction, but actually scratch that. It's the very near future of hydration technology. I really hope this explainer gave you a whole new appreciation for what's sitting right there on your counter. Keep learning, stay curious, and I'll see you next time.